see this one will go here, this will go here, and this will go right over here. So that means that this vertex will be connected to these two vertices at the base. You see? Creating here a side face as a triangle. Now, what else? The top face here will be connected to the top, to the bottom face, correct? Now, the inside face, here I don't like the way the diagram turns to be. 1 second. I will just do it on purpose a little bit more long here. Okay, let's suppose that goes like this. Okay, because the back face will be connected to this one. And the other vertex will be connected to the bottom face. I'm not sure if you guys realize what's going on here. So, you see, we have, let me take things this way. Each vertex of the top face is connected to a side at the bottom face. This is a continuous side line, and this is continuous because you may see it. Okay. Yeah. And so this vertex is connected to this face, this vertex to this face, and this vertex to the other face. Okay, so we want to calculate the volume of T. So T is the convex hull. Okay, and we want the volume of T. Well, it's not that easy to see what's going on here, but it's easier if we realize that, you see, this is an equilateral triangle. So we have to see what remains constant from one diagram to the other one. What can I introduce as a constant? Probably the best thing to see is here. What happens if you have this equilateral triangle in the plane? This is the equilateral triangle in the plane, okay? And how about you rotate this triangle about the center of the triangle with 180 degrees? Okay. Okay, 1 second. So if we rotate this triangle about the center with 180 degrees, look, the triangle turns to be something like this. Is that correct? In the plane. If I rotate the triangle, rotate the equilateral triangle about the centroid with 180 degrees, you get this, correct? And that means that the two triangles create what I call a regular hexagon here. It's normal to be a regular hexagon because look, they create 6 central congruent angles, okay? And considering that, let's look at this diagram that can help me in the space as well, in 3D space. Well, if I fill in the hexagon here, and here, well, then let me place it on the bottom as well. So we get this this prism, right, having, you see, this bases. So the two, let me just remove this option, okay. Having the two bases, the two regular hexagons. Look. And this and this. But I will not overcharge the diagram. So this goes in the very back and this here in the back as well. Okay? So what I'm trying to calculate here is the volume of the T, the convex hull. Now it's important to see that diagram originally as well, because the hexagons that I created there can be identified in the initial diagram as well. And here. So that means that the prism P, right? Initially the prism P could be cut in a hexagonal prism. Okay, so I'm not sure if you guys understand what I'm saying. The idea is that I need to calculate the volume of P. So how can I calculate the volume of P? I'm going to take this diagram on the other page and we're going to try to see how the volume of T can be easily calculated. Let's see. So if things are not very clear here, I will try to clear a little bit the diagram. So imagine that you have that equilateral triangle. The triangle was all rotated to 180 degrees. Okay, and now we have these sides over here that go this way. Okay, and then this is related here, it's connected here. Okay, that will be connected in the back. This is connected in the back. And this is here. Is it more clear now? This is the T shape that I need to calculate. Okay, and as I said, I can add here on this diagram those hexagons that will help me to create a hexagonal prism here. Okay. There you go. So this is our prism. This goes with this. Okay, I need here on the bottom as well. Does that make sense? Are you guys okay with what I'm doing here? I have one edge here and another edge should be right over here. I think this is more clear, okay? So that means that the volume of T can be written as the volume of the hexagonal prism that I initially considered, right? And from this volume, I need to subtract 6 times the volume of one piece like this of a pyramid having the base equal to an isosceles triangle. Let me see, maybe it's clear here. Maybe here you can see very well this piece. And all these pieces will be congruent, you see? So I will say that is the volume of the hexagonal prism minus 6 times the volume of the prism A, B, C, D. A, B, C, D. Can you tell me if you understand what I'm saying here? Are you good? So